let's try to make a graph of cosecant based on what we know. So we know that cosecant of theta is equal to 1 over sine of theta. And I also know what the sine function looks like, and I have it graphed here below. So how can I figure out what the cosecant function looks like just based on that? Well, I can see that when sine of theta is equal to 0, then the cosecant of theta is equal to 1 over 0. Oh, wait a minute, can't do that. That means it's undefined. Okay. So anywhere where sine of theta is equal to 0, meaning where it crosses the x-axis, I'm going to put in a vertical asymptote. So I'm going to start down here at negative 2 pi. I'm going to put one in at negative pi, oops, and all of these multiples of pi. And that'll kind of help us get these different sections of our cosecant graph. Okay, so now what else do I know? Well, I can do the same kind of thing. So when sine of theta is equal to 1, okay, then the cosecant of theta will be 1 over 1, which is 1. Okay, so where sine of theta is equal to 1, cosecant actually has the same value. So that is going to be where they intersect. So all of the angles where sine of theta has an output of 1, cosecant also has an output of 1. So again, they intersect. The same thing is going to happen at negative 1. So where sine of theta is equal to negative 1, then we get that the cosecant of theta is 1 over negative 1, which is negative 1. So I'm going to draw those intersection points in at negative pi over 2, 3 pi over 2, and 7 pi over 2. All right, well, what else do we know? Well, I can think about, how about where sine of theta has an output of 1/2. So I can see where sine of theta has an output of 1/2 by where the graph of sine intersects the line y equals 1/2. And so where that happens, I can even just draw those points in to kind of draw attention to them. But where that happens, I want to think about, well, what's going to happen to my cosecant function? Well, if sine of theta is equal to 1/2, and I know, right, cosecant is the reciprocal. So cosecant has to have the reciprocal value. So 1 over 1/2, I know is just 2. So now at these angles where sine has an output of 1/2, my cosecant is going to have outputs of 2. And then the same thing is going to happen where my sine function has outputs of negative 1/2. So again, I'm just kind of estimating that in there. Then my cosecant function is going to have outputs of negative 2. So if the sine function is outputting negative 1/2, the reciprocal of negative 1/2 is negative 2. And so I can place that in there. Now, how do I know what's kind of happening outside of that? And I'll change these to blue just to be extra consistent. Okay. So how do I know like what else is happening? Well, let's think about when the outputs of sine are really, really close to 1. Okay, so when sine of theta is about 1, okay, then like really close, think about what does cosecant of theta look like? Well, 1 over something that's pretty close to 1, so about 1, is going to be about 1. Well, where does that happen? Well, that kind of happens in these little areas like here, right? Right around that value, the sine output value just dips barely below 1. And so then my outputs are just like kind of barely above 1 there for cosecant. Right? 1 divided by something just smaller than itself is going to have an output just bigger than 1. Okay? The same thing happens down here. We get that kind of symmetry in the graph here. So outputs that are just a little bit smaller, okay, so like these outputs here for sine function are just a little bit smaller than negative 1. So then those outputs, right, by smaller I mean kind of towards the positive, then those outputs are going to be a larger negative value in terms of the absolute value. Okay, so I'm going to start to see that I have this nice kind of cup shape here that's going down. and then the ones on top are just springing from the top like that. So cute. Boom. Okay, so that is a little sketch of our cosecant graph, just based on what we know about sine. So let's look at the domain. All right, some things work and some things don't work, right? So like I see that I have these asymptotes at multiples of pi. So I really want to define cosecant by what is allowed, what is not allowed versus what's allowed. So many things are allowed, but multiples of pi are not allowed. So I'm going to say the domain is, here I'm using theta, so I can use theta. So all theta such that theta is not equal to n pi, where n is in the set of integers. So theta cannot equal n pi, where n is in, this means like belongs to, and then this big Z here means the set of integers. Okay, what about the range? Well, when I look at it here, the cosecant graph is really only the blue, so none of the sine is allowed. So if you just think about what happens, well, I have cosecant graph down here, but it stops at -1, right? It can't go that, and then it begins again at 1 and then above that. So for the range, I'm going to have to write this as -infinity to -1, stop there and include it, union, pick back up at 1 and continue on. What about even and odd? Well, even and odd, is this even or odd? Well, I can see that it's not reflective across the y-axis, or else I'd have something like this, but it's not there. But I do see, like, if I take this cup shape here and I rotate it around the origin, it would land on this piece here. And this piece here would rotate back up and land here. So this does have that rotational symmetry, so it is odd. And it just inherits that from the sine function. So this is odd, so I can say the cosecant of negative theta is negative cosecant of theta. And then what about the period? Well, what is the length of a cycle? Well, I can see that this takes up pi, but its next shape is pointing down. So that's a new shape. So we have up and then down, and then I just start again. And so it takes 2 pi. So it really just inherits the period from pi.